Hello, and today's webinar is going to be about high hydrostatic pressure processing. From the outset, I'll say I'm going to try and focus on the microbiology of HHP, which is really less well understood than the actual technical side of high pressure processing. Certainly high pressure processing has really come to the fore in the last few years as people seek non-thermal processes as an alternative to thermal pasteurization, and its rise to fame has been in a matter of years, from lab scale to commercial scale. It's only been a matter of a few years, and certainly the regulators and our knowledge of how microbes react to high pressure hasn't really kept up with that pace. But hopefully we can fill in some of the gaps. But more importantly, I think it's a case of identifying where those gaps are, so they can actually be filled in. So in terms of what I'm going to be talking about then, is that I'll be talking about a little bit about the technicalities of high pressure processing, because it'll be good background. And I'll be talking about pressure assisted processes, which some people think high pressure is encompassed in one sort of technology, but it isn't. It's like a lot of derivatives, and they all have certain differences. So I'll be talking about high pressure processing and the units and all those pressure assisted processes. I'll then be talking about the mode of inactivation. We certainly know parts of it through studies, but there's a lot we don't understand. And that lack of understanding really comes to when we come to looking at different microbes, seeing what's the relative resistance of those. Because as we'll see, there's a big variation, not only among different genera of microbes or different microbes in general, but also this interstrain variation, which makes validation and finding surrogates really difficult. We'll talk about that. We'll be talking about what intrinsic, extrinsic factors affect pressure resistance of microbes. As we'll see, some promote inactivation, while some are actually protective against the microbe. The search for surrogates is always on, and surrogates are really required in order to validate and verify processes. And we'll be talking about what advances have been there. And then we'll end up talking about regulatory issues, because as I mentioned, high pressure in a lot of ways has outpaced the regulations, and it's only round up now we're starting to figure out what regulations should be actually imposed. And we'll be looking at differences between Europe, Asia and North America and New Zealand, because there are differences in philosophy when it comes to regulating high pressure processed products. And we'll end up with future trends and research needs. So if we go back in history, there's nothing new about high pressure and its antimicrobial activity. Certainly the studies of Roy and Hyde within the last part of the 19th century demonstrated that certain products could be, the shelf life of certain products could be extended by applying high pressure. Now, illustrated here is an example of a high pressure unit. As you can see, it's very small volume for a start, and you can see some of the intricacies of how some of these joints won't be able to take much pressure. And I don't think these systems would have got above 100, maybe 200 megapascals. I couldn't even imagine getting that far. But it was a curiosity. Oddly enough, the first product to be actually high pressured was milk, which was apt because people are looking for non-thermal preservation of milk and a way to get rid of pathogens in raw milk to make it safe, and fresh produce as well. But as you could imagine, these units are very small capacity, they were unreliable, one would say hazardous. And at the same time, we had thermal processing coming to the fore, so thermal pasteurization, canning and sterilization. So it's clear that that was an easier route to follow. So the high pressure technology just went in a different direction, and obviously thermal processing took hold. So the direction the high pressure people went is in chemistry. So if you put carbon under high pressure, you make synthetic diamonds, and even though these wouldn't fool you in the jewelry shop, they're very good. Obviously diamond cutters are very good, and we use diamonds for protective coating. So high pressure was a very good way of making artificial diamonds. And also ceramics from silicon nitride. So these ceramics were novel in their properties, maybe durability, high thermal insulating properties, alloys and intermetallic compounds. They were very good semiconductors and had novel properties. As you get into pressure, you get very novel chemistries. So a lot of the companies that are into the high pressure processing actually can trace their origins to literally synthetic diamond producers, because this is where the high pressure technology really took hold and really took off, because it was high value, and really this is what spurred the advances in the high pressure technology, which subsequently was applied to the food industry. So in terms of high pressure applied in the food industry, the first products ever produced were actually in Japan. These were fairly safe products, with fruit juices, high acid, jam, obviously high sugar, fruit, purees, etc., low acid again. And you also looked at tenderizing meat, not decontaminating meat, but tenderizing it, which pressure is good for doing. So these were only for shelf life extension. They weren't for pathogen reduction, and there was no issue about them. They launched on premium products. And soon after, in France, the first orange juice was launched, which was high pressure processed. Again, it wasn't a pathogen reduction step. They were basically just looking for extended shelf life. So in these early sort of examples, it was a case of just extending shelf life, no real issue about pathogen reduction. Now, the real breakthrough, I think, in high pressure was the humble avocado. And if we look at how high pressure is going across the globe, it's to do with avocados. So anybody who knows avocados know that if you cut them, they'll brown easy, they'll go soft easy. The shelf life is very short. But what they found was when they high pressured it to make guacamole, which is obviously from avocados, not only did they stop the browning, they stopped the softening, they inhibited these enzymes called softening and browning, and they also reduced the microflora. So they got a product that was from a few days shelf life into 4 months shelf life, and it was all fresh, nicely packaged. And certainly, as we'll talk about later on, is guacamole can certainly be looked at as the one that led the wide adoption of high pressure processing across the globe. In '99, they found that pressure could actually is an efficient way of suckling, which essentially is the removal of shells. Previous to that, it was a manual process, very inefficient, certainly with high pressure, which is only about 200 megapascals, no more than that. They could efficiently extract the meat from shells, therefore increasing efficiency with the added advantage of increasing the shelf life. So certainly a lot of seafood processors adopted that technology for that reason. Now, as we went into the mid-90s, obviously it was a big food safety scares coming every 5 minutes in those days. The regulations were overhauled in 1995 with the publication of a white paper. And this white paper was really essentially just saying we need pathogen reduction technologies. And in 2000, there was a Listeria policy launch, which essentially meant those interested in RTE meats, deli meats, must have a pathogen control program for Listeria. Now, the options were fairly limited. You had hot water, where you put the pre-packed deli meat into it. Basically, you had to leave it for so long. The quality of the product suffered. And so there was a lot of interest in introducing it to deli meats as a pathogen reduction step. As you can imagine, the regulators then really started getting concerned, saying, well, shelf life is one thing, pathogen reduction is another, and there was a lot of barriers put into place. And the early adopters of high pressure processing for pathogen reduction will probably tell you a good story about how many years it took them and at what cost it took them, but they finally got it approved. And so what we were finding in 2007, well, even before that, there was an adoption of high pressure to control Listeria and other pathogens and get this extra shelf life extension. One of the motivations for doing it was to remove additives, but as we'll talk about later on, you shouldn't view high pressure as a replacement for additives. It's a bit like irradiation in terms of you can reduce the microbial level, but you need extra hurdles there to stop anything that survives from growing. And then 2009 was a big growth in the fruit juice industry. Certainly some of the early adopters have done very well since then, and certainly it's one of the leading products we have today. Get the raw quality without any adverse effects. So getting in a bit of the technicalities, obviously pressure is measured in different units. The main ones used in high pressure processing are megapascal, the megapascal and the PSI. Typically everyone likes to use megapascals, but I've seen bars, I've seen kilograms, I've seen pounds per square inch. So everybody uses different units, but certainly megapascals is the easiest one to relate to. And just to give you an idea about pressures involved, if we think about 1 megapascal is nearly 10 atmospheres, we're talking about 600 megapascals for a pathogen reduction step. So the pressures are intense, and it's likened to 3 elephants standing on a dime. So very high pressures. So as I mentioned, when the high pressure companies were developing their systems for making things like artificial diamonds, they had vertical systems. So these were vertical chambers where you put in the whatever you wanted to process, and then you took it out again. Obviously that's incompatible with the modern food industry, where they like to have a nice flow of product. And so what you'll see is some of the early systems are actually vertical chambers where they're literally loaded into, but most of the modern systems are horizontal, where you can put the tray with a product into the chamber and then take it out the other end. And there's also other materials handling tricks to do as well, which I'll talk about later. But for now, it's important to know that the differences between the different processes. So high pressure processing pasteurization refers to a process which is non-thermal. So you're typically looking at definitely temperatures below 40 degrees C. And it's designed to reduce microbial counts and obviously decrease pathogens by a certain amount, 5 logs, for example. But you get residual survivors, just like milk pasteurization. But that's very different from high pressure assisted thermal sterilization. So in high pressure assisted thermal sterilization, the temperatures can get up to 100 degrees or more, and you apply pressure at the same time. And you may be thinking, say, well, what is the benefit of using high temperatures and using pressure? Because isn't the benefit of pressure the fact you don't need to apply thermal treatment? Well, with high pressure assisted thermal sterilization, what you have is a process where you can apply these high temperatures but retain some of the sensory quality of the product, relative to, say, canning. So it gives you shorter thermal processing times and much more retention of the sensory qualities. And as we'll talk about at the end, really I think high pressure assisted thermal sterilization is the way it will go, the industry. And then we have a system called high pressure homogenization. So this is really designed to make stable colloids, and some people are starting to report saying, well, in addition to that, it actually has pathogen reduction properties, which it does. The process involves applying a pressure around about 300 megapascals and pushing a liquid through a very small orifice. And when you get the release of the outside the orifice, you get a big pressure drop. It causes cavitation, which basically disintegrates cells. And the other sort of process going on is by applying the pressure, you're starting to add heat to the system. So in actual fact, the main mode of inactivation by high pressure homogenization is through heat inactivation. But the main issue with it is you can't really control the temperature, it's what it is. And therefore you can't just simply say, well, let's forget about the high pressure units, go for the high pressure homogenization. It's not equivalent at all. It's a very different system, just to be aware of. We get other pressure assisted processes, and these are basically adding combinations. So you can apply gamma radiation with pressure. Again, collectively they have an additive effect, some say synergistic effect in activating microbes. Alternating current pulse electric field. By applying pressure, you weaken the membranes, which makes the efficacy of the pulse electric field more efficient. Ultrasound, very similar. You basically sonic waves, and by using pressure, you're destabilizing the cell so the ultrasound can follow through. Carbon dioxide is an interesting treatment. When you put carbon dioxide under pressure, you form carbonic acid, caustic soda, and it's a very good antimicrobial. Um, it's not for every product. For example, if you use it on meat, it tends to use these white spots, but certainly you get an increased efficacy due to the generation of carbonic acid. It's used in blanching without water because, as you know, blanching is to deactivate enzymes in hot water. By using pressure, you deactivate the enzymes by pressure alone, so it's a non-thermal. So you get the sensory characteristics retained and an enzyme inactivated, but it's only certain enzymes, as we'll talk about later on. So pressure-assisted dehydration is where the pressure is applied and it breaks the cells of what you're drying, therefore making it more effective. And a bit like frying, you're compressing the product so it takes up less oil. And you can do it for extraction because you can press for example, plant cells to extract what's in them. And as we know from our high school days, freeze-thawing is that when you apply pressure to a system, you alter the freezing point and the thawing point. So it's used again to retain product quality in that respect. Now, one of the big areas that's coming up or is being researched is about using high pressure to gel meat. So when we make processed meats like salami, for example, what we're actually doing is we're denaturing the meat proteins to make them into that characteristic structure. So previously what we used to do is use salt. So you add high salt to a product to denature the proteins to make a salami, for example. But with high pressure you can get the same effect without salt. So as you can see, there's a lot of benefits from using high pressure of meat because you can get the same structure with less salt, and as we all know, salt's not good for us and people are trying to go towards low salt products. So that's one application. And the hydrodynamic pressure explosives is, well, this is a system which uses gigapascals, so very, very high pressures, and it causes these sonic waves or shock waves to go through the system. I don't know any commercial process using it, but certainly it's a treatment that's being looked at. So the actual process, and I'll be focusing more on high pressure pasteurization in this talk, is that the food has to be packed in vacuum packs. It can be done in MAP. Having air in the packs can be an issue in terms of the pressure buildup and buffering capacity, because if you think about a diver in a dumbbell, they literally go down in an air-contained vessel, which can protect the person inside from high pressure. And if you can imagine the food system, it can protect the microbes from high pressure. But it has been used with MAP. I've seen carbon dioxide atmospheres, for example, used in good effect for certain products. But usually the vacuum packed, and they don't have to be always vacuum packed. I've seen systems where they make special holders where they can process 50 or so kilograms of product in a special chamber, but obviously you don't want it mixing with water, so it's a kind of a chamber that acts like a pack but much bigger. So the product is bought in. It's a batch process, which is not really compatible with continuous production, but there are robotics now which actually can do materials handling to facilitate that, so you don't have one person packing, unpacking it. So once it's packed into this sort of torpedo chamber, the vessel's filled with water, which is a non-compressible liquid. The pressure is applied by hydronic rams and intensifiers, and the pressure treatment's applied for a certain amount of time. And that sort of time, even if you've got a 3-minute processing time, it could actually be 15 minutes because you've got the compression rate to build up the pressure, which can, in older units, take 15 minutes. And decompression is quicker, but it also can take time. So even if you're doing a 3-minute process, you could actually find that the process a cycle could take 15 minutes. So once it's been high pressure processed, the product is unloaded and the next one comes in. So what we have then is a batch process. Like I say, the technology is going towards developing higher compression rates and quicker decompression rates to reduce the cycle time. A lot of the modern systems actually work very well in that respect. They've got it much more quicker, and as we'll talk about, there's different volumes now, which even makes it more compatible with the modern food processing cycles. So, as I alluded to, the reason why high pressure is called on because it gives you a non-thermal inactivation of pathogens, whereas thermal processing brings out change, is expensive. Non-thermal processing retains the sensory qualities, and this is important with things like juices, where you depend on some of the enzymes or perceived enzyme benefits, whereas they would be lost in thermal pasteurization are retained in here. So you get an extension of shelf life through reduction of the microbial load. Sensory qualities I've mentioned. You get retention of nutrients. You do get some vitamin C loss, for example, and vitamin B's, but certainly not to the extent as thermal processing. And you can induce textural changes. And some of these textural changes are beneficial, as we talked about gelation of meat. Other times it's not so good when it coagulates proteins and takes everything out, but that's product dependent. And it's a food processing aid, so no need to label. I know a company that wanted to label their product high pressure process, but it didn't go far. The reasons being that people didn't really understand the process, and but as a process, I think it's got more support than, say, radiation, which isn't too bad. And it's a very versatile process in terms of most foods can be high pressure. There are certain exceptions, for example, raw batter mixes. If you high pressure that, you end up with a pancake at the end. And some neutral products, because of the effect of pressure on proteins, it can coagulate and drop down, so affecting it. But certainly a lot of foods have been high pressured, and most are compatible. So in terms of equipment, there's 4 main providers, but there's about 9 I know of in total. No doubt there'll be others as well as the process continues. The main leaders are Hyperbaric, who are Spanish, and Aver, which are Swedish American. So as I mentioned, both these companies made their sort of fortune making things like artificial diamonds and alloys and things like that. And they were the leaders coming into the process. These were the pioneers. And at the same time, Multivac were there, which was from Germany, a nice piece of German engineering. And the sort of new system on the block is the Cafe, which is from China. Very similar design, but the big difference with this one is that it's substantially cheaper, or less costly, should I say, than the others. And when you are saying, well, which system should I choose? It's a bit like a car, I guess, in terms of you have advantages, disadvantages. Certain companies have better support when you're doing your validation trials or see if it's suitable for your process. Some have better maintenance plans, etc. But I won't go into that because obviously that gets a bit too commercial. But there are subtle differences, but these are the sort of main players. And really what the industry is going towards is, as I mentioned, high compression rates, rapid decompression rates, shorter cycle times. And the other part of it is the capacity. So we see systems getting larger and larger, 600 litres, 700 litres, 500 litres. And also being able to use it in combination with temperature. Because as I said, I think they're looking to the future when certainly this high pressure assisted sterilisation comes into play. So most of them do that. Multivac I'm not sure about, but this is where the systems are going. Now there are lab-based systems which have come down in cost to a degree. Like an average 50 litre high pressure unit will cost you around about $1 million, maybe a bit less. But these systems have low capacity, usually about 3 to 8 litres. As you can see, they're all vertical, and so these used to come in around about $250,000. But the big issue with them is what we don't know is that obviously these compression rates, cycle times are very different to that of commercial units, and there's been this question mark saying how can these results we get from lab-based scale systems relate to commercial scale, and there's been very few studies. There's been research that suggests sometimes you get better kill in bigger systems, some less. So it's one of those sort of open questions that haven't been answered yet. So in terms of mode of inactivation, well, we know by thermal processing that it's a fairly instantaneous effect. You thermally process the cells, the heat denatures proteins, denatures membranes, degrades enzymic pathways. But with high pressure, it's a bit different. It's what we call a slow death. We basically deprive the ability of the cell to make energy, make cell structures and divide. So when we apply moderate pressures around 200 megapascals, the first thing that goes is this ribosome disassembly. So ribosomes are the protein factories of the cell. So what happens is that once your ribosomes are dissociated, they can't produce new proteins, you can't produce new enzymes, new cell structures. But at 200, that's reversible. So once the pressure is relieved, everything goes back to normal and the cells are fine. When you get to 300, this is the sort of mark. This is where irreversible changes start. So one of those changes is where the proteins in the cell membrane, which transport nutrients, generate energy, they become dissociated from the membrane. So in effect, the poor cell can't import any nutrients to metabolize, produce energy. The ribosomes have gone because you can't, protein synthesis. The enzyme generating enzymes are also, ATP generating enzymes are also inhibited. So you're basically depriving the cells of nutrients and eventually and ultimately deprive them of ability to generate energy, destabilize the cell membrane, and so the cell's left to die on its own, which typically takes 72 hours or longer. So this is the important thing about high pressure, is that when you suddenly apply high pressure and then take the samples straight after, you'll notice the log reduction in pathogen numbers or microbial numbers is different if you leave it 72 hours, because it's got a lot, the cells can't recover at all, where they can potentially recover if they're given a nice agar medium. So typically then, when you're doing a trial, you tend to just leave a waiting period afterwards in order to get the real extent of the kill. So the factors that affect the high pressure resistance of cells varies, and a lot of these still aren't unknown. Well, we certainly know its microbial type. Not only is it between eukaryotes, prokaryotes, but even the genera and strain. pH, we know that high acid supports increased efficacy. We know water activity protects cells, or the conditions of water activity stimulate the stress response in bacterial cells to prevent them being affected by high pressure. Pre-stress, so if you, for example, cold shock or osmotic shock cells, they tend to be more bar tolerant and resistant compared to cells taken straight from a media, growth media. Obviously the pressure is important, as we talked about in the previous slide. At low pressure you get reversible changes, but as you go up the pressure scale, those changes become irreversible. The time of processing is actually less significant, as I'll tell you, but certainly you do get some added feature with time, but basically it's the pressure rather than the time. Temperature is important. We talked about thermal sterilization, but it's interesting, there is an option which we'll talk about where you shouldn't go with high pressure because the actual cells get more resistant. And also the post-treatment handling. How do you store the product? What's the matrix it's in? Can also all influence the ability of that cell to either recover or die, and the log reductions recorded. So in general, eukaryotics are definitely more sensitive than prokaryotics. So eukaryotics like yeast, mold, they tend to be quickly taken out by pressure due to the complexity. The general rule is gram-positives more resistant than gram-negatives, which doesn't really hold true. Some E. coli 157 strains, for example, are very pressure tolerant, whereas others are very sensitive. Cocci versus rods, people have made this association, say, well, a cocci just morphologically is more resistant to high pressure than rods, but that's not really true as well, but it's a generalization. So when we look at different pathogens, for example, we find a big spectrum of sensitivities. So Vibrio, which is found in seafood, tends to be most sensitive. It just needs a few hundred megapascals to actually cause inactivation. Whereas Staph aureus, which we know is tolerant to low water activity, is very bar tolerant. So we get this sort of separation. Now in terms of spoilage, when we vacuum pack foods, obviously lactic acid bacteria are our main sort of concern. And unfortunately for us in one way, lactic acid bacteria show high pressure tolerance. But this isn't a good way. It means that they could be useful for useful surrogate organisms. So rather than using pathogens in our processing plant, we can just get lactic acid bacteria instead. So when people have tried to model high pressure processing, they've tried to adopt those processes from thermal processing. And we all know about D values, say the time it takes, a set condition, pressure in this case, to cause 90% reduction in levels. And we know the Z value is a change in pressure to cause a 1 log difference in the D value. The trouble is though, as we'll see, very rarely do you get nice linear responses in that inactivation due to the fact of the nature of the mode of inactivation, which, as I mentioned, unlike thermal processing, which is instantaneous, high pressure is more a slow death, so it doesn't really follow first order kinetics. And this just gives you an idea about certain pressures. So for example, these are the spores. We need high temperature. Basically running pressure at low temperatures doesn't do anything. And we can see a sort of spectrum. So Bacillus anthracis has very high tolerance, whereas Bacillus spores in general has low one. Clostridia vary, but it's fairly tolerant. And we'll be talking about spores towards the end. But the more interest at the moment is looking at these other pathogens. We see Vibrio, for example. Vibrio is very sensitive to pressure, so it's got a very low D value. Whereas ones like E. coli are very robust to pressure. And Salmonella is fairly sensitive and immediate. Listeria shows different levels of pressure resistance, but certainly is almost akin to E. coli. Then the one at the bottom is actually a yeast. It's a Zygosaccharomyces. And Zygosaccharomyces is very interesting to people in the fruit industry because this yeast is the one that causes spoilage. Very resistant to sulfur dioxide, very resistant to thermal processing, and so when you get issues, it's usually with Zygosaccharomyces in fruit products, and its pressure resistance is almost like the E. coli. As I said, the eukaryotics tend to be more sensitive. So this is just a generalization scheme about the sort of spectrum of resistances you find. So we've got spores and these different symbols. These at these sort of end over here, these are spores, and the thing is that they're more pressure tolerant, which you expect, but also what you've got to note is a big variation even between strains of the same organism, and that's one of the issues. There's no hard and fast rule to say you can't even predict this one will be pressure tolerant, this one won't. So there's a big spectrum, and when we come to the more the bacterial ones, you can see the orange triangles here, and this is Vibrio. As we mentioned, fairly sensitive, but even with Vibrio you can see some are very sensitive whilst others are very resistant. And E. coli, as I mentioned, is fairly tolerant depending on the strain used. So there's a big variation in terms of resistances. So the effect of temperature is an interesting one because everyone believes saying, well, the warmer the temperature, the better kill you're going to get, but it doesn't follow with high pressure. So with high pressure, in actual fact, the colder it is, sometimes the better, because what happens is you get a good kill at 4 degrees C, as you would do around about 58 degrees C, but obviously with the added benefit of not having the pressure, whereas intermediate to that, the actual efficacy of pressure is less. And there's this sort of spectrum, this range about 20 to 30 degrees C, where you actually decrease the efficacy. And this is found for things like Listeria, Campylobacter. But oddly enough, for Lactobacillus, it's opposite. So essentially, the more warmer it gets, it follows this linear relationship up to the point where obviously then it gets firmly inactivated, due to the fact the temperature is. So the temperature you actually operate your high pressure unit as will affect the efficacy of the process. And most processes work around in the sort of 410 degrees C, and certainly, but when we get to the higher temperatures, that's more thermal assisted sterilization, which we'll talk about. But the big thing, it does reduce the sensory characteristics. So the golden rule is never work between 20 and 30 degrees C when you're doing high pressure processing. Now, as I mentioned, people have tried to model the actual inactivation kinetics, and the problem they find when they're doing it is these diphasic inactivation curves, or multiphasic in some cases. So what we see when we do a pressure trial, this is Staph aureus, which is a classic example, some strains have a shoulder, whereas other strains don't have any shoulder. And this shoulder is really the ability of the cell to repair sublethal injury. So when we plate it out onto they're affected by pressure, but it's irreversible damage, or reversible damage, so they can repair themselves up to a point, and it gets beyond their capabilities, then you get a nice reduction. But then you get a tailing effect at the end. So this tailing can be due to the selection of mutants, which are bar tolerant. It could be cells within a population, because we think populations even grown in the lab are homogeneous, but it's not true. It's heterogeneous, and so you could be selecting for those. There's other issues about detection techniques, but you usually get a shoulder and a tail. But not all strains. So these are different strains of Staph aureus. You can see there's big variation in terms of the efficacy. So it's when you're trying to model this, you're trying to do all these variables at once. But after saying that, models have been produced based on these diphasic inactivation curves using Wilbur and other multivariant models. But the problem is you not only get different responses depending on the strain you use, but which food system you're in, as we'll talk about. Different food systems support different efficacy or different log reductions, and hence it's product specific. So you can get one product specific, but you can't take, for example, one for high acid juice and expect that to cover every high acid juice you have, or every pathogen, or even strains within that pathogenic group. So what is bar tolerance? Well, bar tolerance is our sort of Achilles heel, if you like, of high pressure pasteurization, and some of the least understood. So we do know that we get variation between genera. So E. coli is very high pressure tolerant, Vibrio is very sensitive, Salmonella is somewhere in between. But even when we look at genera, one E. coli strain is more resistant to another E. coli strain. So it's a moving target in many respects. And what we know of bar tolerance is that sometimes it can be genetic. So people have suggested about this, what we call high pressure gene, this gene which imparts stress tolerance or pressure tolerance to the cell. Certainly there have been genes identified, and when they're mutated, the mutant does go back to being pressure sensitive, but it's a little understood. You know, people are suggesting, well, it's just one gene of a whole system that's taking place there. I guess more often seen is what we call temporal resistance. So this is where, for example, you'll apply high pressure, you'll get survivors, and then you'll grow those survivors up and see if the actual strain retains its pressure tolerance. And in certain cases there's this genetic mutation that enables one cell to go over generation after generation, improving its pressure tolerance. But in most cases it's temporal. So if you get a population, or you get an isolate from a surviving population, regrow it, you get the same distribution. Some cells within that population are bar tolerant, some are bar sensitive. Growth phase, certainly growing, harvesting cells in the exponential growth phase and pressure run, they'll be more pressure sensitive than stationary cells, which obviously induce stress proteins and whatnot. And talk about stress, the pre-stress is also critical. If, for example, you adapt cells to low water activity, you can bet your bottom dollar they'll be very pressure tolerant at the end. And the matrix effect, which is really little understood. As we'll talk about later on, some cell matrices support inactivation of microbes. So, for example, high acid does, whereas other cells, other matrices such as high salt, high sugar, they tend to work negatively against it. And we'll also look at more little constituents as well, which can look protective or can be additive to the pressure. So this just illustrates really the issue. So this is a Listeria population, well, Listeria, 100 different strains, and I've just tested the reduction at one set pressure and time. And as you can see, some are very sensitive, whereas others are very resistant. And that's just with Listeria, with 100 strains. So you could imagine, which one do you choose for your validation? Which one's the worst case scenario? Very difficult, because there's always another one that you'll see later on. So, as I said, the principle of Bartolerance is not well understood. Certainly people have looked into what we call pressure resistant cells that live deep in the ocean and see, well, how do they survive high pressure? And what they find, amongst other things, is a high degree of unsaturated fatty acid membranes. So people have suggested that having unsaturated membranes makes them more pressure tolerant. A more likely theory is the expression of stress proteins. So what you'll find is in some, for example, Listeria, which are very bar tolerant, they have this deregulation of their stress proteins, so they're produced constitutively, which obviously affects their growth rate as such, but they're more liable to resist stress if it's imposed on them. So deregulation of RPOS in gram-negative, sigma B in gram-positives, these are the switched off stress proteins. In E. coli, there's been genetics, a gene associated with high pressure, as I mentioned, but the most common sort of theory is that they accumulate protectants. So when a cell is subject to high salt or sugar, what they have to do is stabilize the cell structure, and they do this by importing glycerol, glycine, betaine or trehalose. So what these sugars do is actually make the cytoplasm of the cell much more viscous, i.e. stabilizes it. And so people suggesting that it's these osmoprotectants that's key. So if you've got a product which has got glycerol in, which I don't know if it will or not, that's likely to protect the cell rather than act with pressure. Now there is this sort of correlation saying, well, the cost of bar tolerance is at the cost of virulence in terms of an E. coli 157. If it's bar tolerant, it's going to be less virulent, but there's been too few studies to demonstrate that. Some people say the reverse in actual fact. And there's other issue about selecting for a subpopulation. This really is very common in E. coli. What you'll find in E. coli is that the population is heterogeneous, and it does that for a reason, in terms of it wants to protect itself in case you get adverse conditions. You've got at least a part of the population that will survive. And so what you could have is a selection process where the pressure sensitive ones die off, leaving the pressure resistance one, which then can be recovered on plates and outgrow. So these are all the theories, but again, it's a lot of knowledge gaps. So, but stress resist tolerance and stress expression of stress proteins is a very significant factor. So when we impose sublethal stress, what we get is we get damaged cells, but those cells can express proteins which shore up their cell structures, like protein synthesis, protects the DNA, membranes, and these become stress adapted. So these are going to be very resistant to pressure compared to a healthy cell. Now, obviously, at some point we impose so much stress that it can't be repaired, and that's where we get irreversible injury to the cell. It can't express anything, so it slowly dies. But certainly pre-adapted stress is key, and again, this is a real problem for validation, because saying, well, what stress do you apply? That is the key thing. Now, as we've talked about, you do get variation even between strain and strain, even within a population of strains. But in actual fact, it's what we call acquisition of bar tolerance. This is where a typical population will be pressure sensitive, but through selection, mutation, they become bar tolerant. That really only seen with Listeria and E. coli. So there's a famous E. coli MF1655, which shows extreme pressure tolerance over generations. I think 80 generations are said. So this is where they acquire bar tolerance. But interestingly, Yersinia, Salmonella, Shigella, Pseudomonas, they don't actually adapt to high pressure. So if you get survivors, they're not going to be any more pressure resistant than the parental strain. But here's one that people don't understand too much, and that's the food matrix. What we do know is if we've got low water activity, it protects them against the cell against high pressure. We know that low pH enhances high pressure. And we also know that membrane acting additives like bacteriocins, lysozyme, essential oils, they help high pressure disrupt cells, and they act synergistically to do so. So certainly these additives are well known and being tested, but what's unknown is about the food protective constituents. So what we find is that through trials we've done, and we've worked with high pressure over 6 years now, and must have done over 100 different products, those containing carrot juice tend to have less reduction than those with no carrot juice. So what constituents in there we do not know, but we also find if we process raw meat versus cooked meat, again the raw meat protects it, and you could say, well, it's the amino acids, the residual sugars, maybe protein, peptides in there that's doing that, but what we find is these are protective against the effects of high pressure. So as I mentioned, we've been working with high pressure for about 6 years now, and we've looked at over 100 different products, and these have been juices, hams, other meat, deli meat products, and even down to gravy concentrates, you name it, cheese, dairy products, etc. But for ease of illustrating the data, we're going to focus on these 4 food groups: the high acid, low acid juices, cured meats, and non-cured. Now, the important thing to remember when we look at these this stage is that we use the same strains all the time. So we're getting away from that strain variation. So we use Salmonella, E. coli 157, Listeria. So the only thing that was different was the food matrix. The recovery, the growth, and everything was exactly the same between trials. So this is what we find. This is for juices. So the first thing that's really evident is the large variation we have in E. coli, for example. So even though it's the same strain of E. coli, it depends on the sort of juice constituents. And Salmonella as well, you know, it's got variation, as does Listeria. So understanding what the effector constituents is going to be very significant, something we need to research on. So these are high acid juices below pH 4.5, but what about the low acid juices? So low acid juice is actually more consistent. We get less variation, but we also get less log reduction, you know, due to the fact I haven't got the aid of pH. But interestingly, they're fairly consistent, which you might think is opposite what you might expect, because with high acid working, you expect it to be fairly uniform, but in actual fact, it's the low acid which are more predictable than the high acid. When we come to meats, an interesting thing that comes across is that cured meats have a protective role in protecting microbes from high pressure inactivation, whereas non-cured meats don't, although, as I say, there are exceptions to the rule. So the interesting thing here with E. coli is that it's more consistent, whereas Listeria and Salmonella, you do get this big variation. And the other thing to note is the pressure tolerance. You can see E. coli is much more resistant than Salmonella and Listeria. Not for all products, admittedly, but for most of them. But with these non-cured meats, again, you have this giant variation. But this variation is skewed a little bit because this bottom figure here is actually raw ground beef. And as I mentioned, if you compare raw ground beef with cooked product, the pressure resistances are very different, you know, due to the fact of the different tolerances. But Salmonella is fairly sensitive, and Listeria is, so you get variation, but I think you can imagine it's very product specific. You can't make generalizations at all. And this is just a confused graph. It's more to do with the effect of temperature, and this includes a low activity food. So these are the gravy concentrates and that. So the first thing that comes out at you is that the low water activity products are much more tolerant to pressure, even if you have extended processing times of 10 minutes or so. Now they've got different symbols here. The crosses relate to Listeria, the triangles relate to Salmonella, and the circles relate to E. coli. And the thing that comes across, isn't it, is that you get big variation in terms of tolerances depending on the product. And really what it also illustrates is that the time of processing doesn't have that much effect. Certainly you do get slightly higher inactivation by using extended processing times, but the returns are very low compared to changing the pressure. So to distill all those results then, what we find with high pressure processing of these different products is we find a high variability due to the food matrix alone. As I keep mentioning, is the strains and methods are all the same for all these products. High acid juices want a higher log reduction than low acid. Cured meats is harder to inactivate compared to non-cured meats, and low water activity, as we said, they might not support pathogen grow afterwards, but certainly they don't aid the inactivation. And what we find then is that processing times, although you might think extra processing time would be beneficial, which you do get a slight increase, but certainly the returns are very small as the longer you go. But the big thing is the product constituents influence the efficacy of pressure, and that's what we don't know. Really, we can make generalizations, but at this moment we're not sure which promote it and which work against pressure. So, as I mentioned, when you've pressurized the product, the cells are basically incapacitated. They've lost the ability to synthesize proteins, generate energy in many cases, and even produce enzymes, etc. But the fact is that you can get post-lethal recovery in certain circumstances, certainly not in high acid. So when you're in high acid, you're basically you're going to get acidified cytoplasm. You've got no energy to transport the protons out, and therefore you're going to aid the post-treatment lethality. Low water activity actually promotes survival, so they'll persist for extra longer time. Low temperature actually also promotes survival, so the instinct is always to keep things at refrigerated temperatures, but in actual fact, room temperature, the cells can't repair as effectively. But obviously we can't store foods at 20 degrees C due to the risk of spore germination, toxin production, so we have to keep them at 4. But as I said, what we also found is certain food constituents seem to aid recovery, and we don't know what constituents they are. All we know is products containing coconut tend to promote recovery. Ginger, which we use as a sort of antimicrobial itself, that protects cells, enables them to recover, and starch as well. These polymeric glucose units, isn't it? They protect the cell and aid recovery. But what we find in all our sort of studies and what other people have written is that the pathogen recovery rate is fairly rare. It's very rare do we actually get a recovery of a pathogen. It only happened once, and I'm going to refer to that in the next slide. But mainly your issue is spoilage bacteria, be it lactic acid bacteria or spore formers. They're the ones that tend to recover and outgrow and spoil the product if you haven't got additional hurdles. But the only one product where we did get pathogen recovery is with hash browns. So hash browns, obviously a potato product which is breaded, due to be fried, and so with high pressure discs, the initial log reductions were fairly good, but above 5. And with E. coli and salmonella, we did get some persistence after the event, but eventually died off when it stood at 4 degrees C. Now the problem is though is that Listeria, which is a psychotrope, can grow at 4 degrees C, and it's the only time the pathogen actually recovered and grew to dangerous levels after the high pressure treatment. But in most cases the pathogens simply just die off. Now, turning to viruses, obviously viruses are fairly significant. Norovirus causes more foodborne illness outbreaks than bacteria put together. And the good news is that they're fairly sensitive. So we can get a good 4 log reduction with moderate pressures. Calicivirus, which is a surrogate for norovirus, that true is also inactivated, but it's interesting, it shows this sort of temperature dependency. So at 20 degrees C, it's much higher tolerant than at 4 or 50. And the other good news is the coliphages, T4 and MS2 phage, are actually resistant. And the reason why MS2 and T4 are significant is that they're bacteriophages, easy to culture in the lab, and because they're more bowel tolerant, they can be used as a surrogate for norovirus. And as we know, viruses aren't alive, they're just protein coats with nucleic acid inside, and the feeling is that the proteins, the capsids, are affected by pressure, which basically denatures them. Now, enteric protozoa is significant. We had a big outbreak of Cyclospora last year, and we also get issues like trichinella, very rare, but it could happen, and toxoplasma, which is a bit more common. But as with your eukaryotes, they're very sensitive. A 4-log reduction at 340 megapascals is sufficient to cause inactivation. So viruses and protozoa are one thing, but the vegetative pathogens and spore former are definitely another. And what the industry has been looking for is a way to standardize the validation protocol. Because standardized protocols are good because it means that regulators understand what reasoning's been in there, and we're comparing everything on an even playing field rather than one person doing one sort of study and another person doing another. So validation protocols, standard ones, are very good for that approval process. But what's the big question mark is, well, what do we measure? Do we simply measure water activity and pH? If we're going to apply stress, what stress should be applied? You know, which strains to use? Like, do we seek the most bar tolerant, and if so, how many strains do we have to test? Can we use a surrogate, which we eventually have to do because you have to relate it to your commercial process? Well, which surrogate do you choose? The inoculation level is important, and contribution of intrinsic of the product. So what we're talking about here is if you've got a high acid product and you inoculate pathogens into it, can you count the reduction due to acidity, which there will be some. And we'll talk about this later, but there's varying opinion of it. Some say no, you have to demonstrate a 5-log reduction by the pressure treatment alone, whereas others show the additive effect is sufficient. Which recovery methods do we use? Do we leave it a certain amount of time before we sample it? Do we sample it within a short time of processing? Again, there's no hard and fast rule. And shelf life prediction, like, can we extrapolate results, or do we have to actually do the whole shelf life of a product, which could be 3 or 4 months? So in terms of what pre-stress should be applied, although it's no golden rule, the general procedure is to use stationary cells because they're more pressure resistant, and also to pre-stress the cells at 4 degrees C before inoculating into the product due to the induction of the stress proteins. In terms of strain to be used, as I said, it's an open question because you get one strain and you've got to prove it's the most bar tolerant. Well, you only can do that by testing more strains. But fortunately, there are sort of two that's coming to the fore, which is C490 and then CTC11994. One of the issues is availability. Where would you get them from? And you know, are these truly the most pressure tolerant you'll find, or is there additional ones there? But these are being proposed. So there have been a big search for surrogates because obviously with surrogates you don't need to use pathogens because you can't take pathogens into food plants, and even in the volumes you use these pathogens on, even with products, sometimes you don't want to use high volumes and have the risk of contaminating a whole pressure unit. So people look at generic E. coli, and certainly there have been E. coli strains that have demonstrated resistance equivalent to that of 0157. Listeria innocua is a good surrogate for Listeria, but as we saw, big variations. Most of it is a good surrogate, other ones it's not. An interesting one is Lactobacillus fructivarans, which has shown pressure tolerance equal to 0157, which is useful, but even then you might not want to bring a lactobacillus into your plant due to the spoilage impact. Certainly MS2 bacteriophage has been used for as a surrogate for enteric viruses and parasites, and its pressure tolerance permits that. But the more interesting research that might be going on, well, it's started, but it's in its early days, is using an enzyme. So we're doing milk pasteurization. We use an alkaline phosphatase as our sort of verification. So we know if we inactivate this enzyme, we've inactivated the pathogens. So what people are trying to find is an enzyme which has got similar tolerance to pressure than, say, an 0157. And as you can imagine, enzymes are good to screen for because it's quick and easy, less expensive, much more rapid. But the research is still in its early infancy, but it's a new way of looking at it. And the problem is then it's very hard to predict, though, which strains will be bar tolerant or not, because we can try and correlate it to things like thermal resistance or resistance to low water activity, but it doesn't always correlate. So there's no way of even anticipating which strains will be bar tolerant, which aren't. based on the fact that we need to run the trials first. So this is some studies we did looking at different surrogates, and what we find is lactobacillus certainly is a very good surrogate for 0157. It shows equal, if not better, bar tolerance, whereas Salmonella, Listeria, again, it could be a surrogate for them, but they're more sensitive. And Saccharomyces, which is a yeast, which is very sensitive, that's not a really good surrogate for the pathogens. But lactobacillus, there's a lot of interest in using those as a sort of surrogate. So, as I mentioned, there's a big issue about inoculation level and contribution of intrinsic factors. So, as I mentioned, this is where, for example, you've got a high acid product, you inoculate it with a set population, you get some reduction due to the acidity, but does that count to all the overall efficacy? And it's very split. In the US, they're fairly receptive to this. They say, well, it's a food safety objective. You've got 3 log reduction in pH due to pH, 2 log reduction due to pressure, then that makes sense to us. But in Health Canada, for example, they don't go for that. They want to see a 5 log reduction of the pressure cycle in isolation. So you tend to have to inoculate more, things like that. So bacterial spores are an interesting one because the Achilles heel, if you like, of high pressure pasteurization. If we're looking to inactivate spores directly, we need very high pressures, certainly almost double the amount we have today. But with pressure-assisted thermal sterilization, it can be done, but you have to use high temperatures with moderate pressures, well, moderate being 600 megapascal, which is the upper limit of units today. But what can happen with spores is that when you induce or you put spores under pressure, you can actually induce germination, very much like heat activation. So here you're just waking the spores up to be receptive. And if there's a germinating agent in there, which commonly there are, you can lead to this germination outgrowth during post-storage handling. And there's been a few theories why we get this pressure-induced germination. Some say the spore coat becomes more permeable, and therefore you can get more germinants moving into the receptors, or more likely it's a reorientation of those receptors. So the thing about spores is that they've got a impermeable outer coat and a cortex, and the receptors due to germination are actually on the inside forespore. And so what happens here is that when there's a germinant present, they bind to these receptors and it produces this sort of cascade effect where lytic enzymes are activated, it degrades the cortex, the core hydrates, the spore wall goes away, the spore germinates. But people suggesting that high pressure could reorientate them in order to have the same effect. So we looked at this research a few years ago, and what we found was that certainly preheating enhances the germination at lower pressure. There is an optimum. So if we do preheating, we get pressure-induced germination around about 250 megapascals. But if we go higher pressure, then the germination rate decreases. We talk about log count reduction, but you should view it as germination. This is where we apply the pressure and then we heat and activate the germinated cells. And from the difference, we can say how many cells have been or spores have germinated. So with no heat treatment, then preheat treatment, what we tend to find is that we get a displacement of this optimum to 500 megapascals. So you can see we're getting into the area now where we commercially process high pressure processed foods at about 500 or 600. And if we adjust the pH, we actually find again it displaces the actual pressure curve. So this is with heat activation, this is without. So as you can see, there is a real risk of when we apply pressures of stimulating germination, which could then cause problems down the road during shelf life. This is just the effect of germination, or this is heat activation time. So what we find with the time of the pressure treatment, should I say, with heat activation, certainly you stimulate the spores to germinate compared to when non-heat activated. This is at 200 megapascals though. So the fact is spores are a big issue. So in terms of endospores and food stems, so really what people have looked at is saying, well, can we use this pressure-induced germination to our advantage? Because we could germinate the spores using one pressure, then actually kill off those germinated cells by using a second pressure. Well, we can't really do that because of the super dormant spores. There's a certain population of spores that retain their viability but don't fall for the trick of germinating, so they tend to outgrow in the subsequent product. And when you're getting into this sort of germination, you can't help but think about Clostridium perfringens, botulinum even, and also Bacillus cereus, which can potentially increase in number, producing toxin which can't be readily inactivated. So really, when people have looked at this, they've given it up fairly quickly due to these issues. So what you really need then in a product, and there is occasions where somebody decided to use a nitrite-free sausage, for example, only to find they spoil because of Clostridium blowing up the pack. So really what you need is an additional hurdle, be it temperature, reducing the temperature to refrigerate. Obviously it doesn't guard against non-proteolytic Clostridium botulinum. Increasing the acidity will, decreasing the water activity will, adding nitrites, or shortening the shelf life from say 4 months to 20 days, and we'll cover an example where that was actually used. So you need an additional hurdle in place to stop spore outgrowth for sure. So with toxins then, there has been work to look at the degradation of toxins by pressure treatment. One of the more successful is pathogen. Pathogen is a mycotoxin, often found in, well, sometimes found in apple juice. And what we found is that you get about 20-20% degradation depending on the conditions used. So pathogen can be degraded, but other ones like enterotoxin and cytotoxin react differently. So Staphylococcus produces enterotoxin, which can cause basically sickness, in very extreme cases, sudden shock syndrome, toxic shock syndrome. What we find with pressure actually increases activity. So this is where you have to be wary about your raw material. You can't expect to have a raw material which is defective and hope the pressure will take care of it. A bit like irradiation. If enterotoxin's there, then it's going to be there at the end. But with pressure, it's actually increased activity. But at least bacteria, the serious cytotoxin is reduced, so we're at high temperatures. So they've been interested in that in high pressure processing of rice, for example. But one of the biggest applications of high pressure, one of them, is enzyme denaturation. And the thing is, we find different enzymes behave differently. So one of the big enzymes is polymethyl esterase. So this is one that causes softening of fruit and vegetables. And we find with apple, you can actually increase activity by applying pressure. With carrot, you can actually cause inactivation, depending on what pressure area you're looking at. With oranges, you get inactivation. With tomatoes, you get increased activity. So as you can see, it's like a moving ball, isn't it? And I'm pretty sure it's to do with how the enzyme interacts with its surroundings. So certainly, certain products with polymethyl esterase, it can reduce activity, therefore enhance the texture of the product. But in other cases, it makes it worse. Polyphenol oxidase is an enzyme that causes browning in apples, for example, and avocado, as we've referred to. And the good thing about pressure, it actually inactivates the enzyme. So you don't need to add sulfur dioxide, you don't need all those anti-browning agents. You can apply pressure, and as we saw with avocado, it really has been the big sort of stimulus of high pressure in the fact that it can prevent browning. Peroxidase, it actually increases activity, causes oxidation obviously. Lipo-oxygenase in avocado again causes softening and browning. It's actually inactivated. So you can see why the avocado people went to it. It's all those key enzymes that preserves it. Allergens, there have been some work with allergens, but certainly nothing really conclusive. Most of the time there's no change. Sometimes, for example, with soybean, there's a decrease in allergenic properties, but with whey protein, it actually increases. But certainly as a allergen intervention, so there has been little research, but certainly what's being published, you would never say, yes, it should be an allergen control. It doesn't do that much. But as I say, it's an active area of research, given that most product recalls is down to allergens in foods. And so what people suggest is that The pressure actually induced, because allergens are proteins, it denatures them, reconfirms them. It can actually cause extraction from the cell, therefore being washed away, so to speak, or it can actually stimulate enzymes to degrade them. But whichever effect it is, by degrading or changing the conformation, you don't get the allergenic effect. So what I'll do is talk a little bit about how to position high pressure foods. Now, it does cost money to do high pressure processing. You're looking at $1 million for a commercial unit. Typically that works out about 10 cents a kilogram of product, which has come down a lot since its early days. But even then, you've got to think, well, if it's going to be a high value, where should I position it? Is it good for every product? Well, milk, for example, which was one of the first high pressure products in the late 19th century, certainly you could see it'll improve safety. You'll inactivate pathogens. It'll be like a raw milk texture flavour. But would people buy that? Well, the question is maybe not. You know, why should they? They've got filtered milk and things like that. And even I would imagine the raw milk people wouldn't say, well, it's been processed. That word processed is enough to put everyone off. So beer and wine. Wine is an interesting one because there's been a move trying to remove sulfur dioxide from wine. So you add sulfur dioxide to wines to stabilise them, i.e. to prevent oxidation, to prevent yeast or lactic acid bacteria growing. And there's been some work on that, but whether it's wine's a big safety issue, well, it's not really in a lot of ways, but it would add value, some people say. Pet foods. With pet foods, there's been a few recalls down to salmonella, and there's been a few. We've done some trials with dried pet food, as you can imagine, have not been so successful due to the fact of the low water activity. But people are willing to pay to protect the pets. You know, it's the way we are. But certainly the sort of food scares with pet foods and salmonella, whether it justifies using high pressure, like I say, it's just really positioning yourself in a different market. But then we come to, let's go to the more high value ones. Certainly organic foods, you know, the ability to reduce additives or no additives, but preserving the quality and nutrients is of interest. The ready to eat meals, rather than having these frozen dinners, it'd be nice to have a refrigerated dinner that you can just put in the oven. Very much like the European model, they really go for these RTE meals. That's going to be a high value product, as is with meats and juices and dressings, etc. So when you're choosing a product, yes, certainly you've got to look where you're going to position it in the market, and is it worth the effort to do it. So in terms of sectors then, as you could imagine, those products which are high value, the vegetables products and fruit and vegetable purees, etc., guacamole being the main one that I keep going on about. Juices and beverages are really increasing now. The ability to have an orange juice which has got the taste of raw orange over and have a 9 month or 4 month shelf life is very good. And we did some early trials with fresh orange, and literally you can pressure it and it tastes as good as day 0 as it does in day 60. Very effective. Meat products as a Listeria intervention. Seafood as an extension is also there, and other products, and there's been a wide variety of them, some more successful than others. But as I mentioned, the thing about high pressure processing is that it's sudden sort of rise to prominence. So it's one of those technologies that went from lab scale to commercial scale very quickly, and it's really been the guacamole, I call it, charge in terms of that's really introduced, put high pressure on the global stage, and obviously people finding other use for it, such as juices and meat products, in addition to seafood. But certainly meat and vegetable products are the ones that form the market, but fresh juices are really coming up. And just as a prediction, it's always hard to predict, but at the rate of growth of the high pressure market, they're looking at about $18 billion market for high pressure products. That's that equates to about $600 million in terms of equipment. And as you can imagine, this is why all these companies are getting on board now, because they can see the market's just going to get bigger, which I think it is. So in terms of global scale, then what we find is that most of the high pressure units are in North America, and there's a very good reason for that. And we'll be talking about regulation soon. And in Europe, where they actually developed most of the high pressure technology, oddly enough, it's not used very widely. It's certainly increasing, but it's more for shelf life extension than anything else. And Australia and New Zealand, Mexico and South America, these are really leading on the guacamole market. So, for example, in Australia and New Zealand, I think it's all guacamole. Japan, jams, jellies. China, guacamole. Thailand is sort of fruit and vegetables, and meat in Czechoslovakia or Russia. I think that's Russia. So essentially, it's not, when we say global, yes, it's starting to get global, but certainly it's not in every sort of city you'll ever go in. Basically, North America, Canada, and the US dominate the market, unless it's sold on other products. But as I said, the other ones are basically fruit and vegetable processing. So the big thing, reason why we haven't expanded high pressure, is the regulations. So when high pressure first came onto the market, it was basically shelf life extension. Nobody really cared from a regulatory point of view. If shelf life's good, that's good for you, you do it. But when you start talking about pathogen intervention, you start getting into food safety, and food safety obviously is a concern for regulators. So because of the large knowledge gaps, as I said, we don't know much now. We even knew less when high pressure was being introduced. We had lots of key gaps of knowledge. So to get over that, what the regulators decided to do is saying, let's call it a novel food. Now, the novel food regulations are really in place to stop GMO, genetically modified product coming to the market. Because it's basically saying, and it's different definitions in different districts, but essentially it's saying that any food that has not been previously applied to that food. So we're not saying high pressure is a novel process. We're saying foods produced by high pressure are novel because they haven't been applied. And does it undergo a major change in the food? Well, we don't know, and therefore, well, it's safe. If we don't know, it's safe to say that you've got to prove it doesn't. So this gave it a food safety designation as well. And when we're looking at novel food classifications, it's up to us, as processors, or the process itself, to identify the pathogens of concern, how effective it should be, and to try and prove that there's no detrimental byproducts. And as you can tell, trying to prove a negative is very difficult. But the big concern was leaching of material or components of the packaging into the product, and a lot of work's been done on that, and there's packaging that's approved now. You have to have pressure approved packaging, but it's a very costly exercise if you want to bring a new packaging. I know someone who spent $30,000 on a study just to try and prove that their product didn't have any leaching. And it's product specific, so you can't say, well, I've got a high acid juice here, that means every high acid juice I've got can be covered by the same classification. No, it's not like that. Product specific. And this novel designation has really been a barrier to implementation. And what does it mean? Well, it means that individuals' products have to be evaluated. There's no designation. You can't be inventive and produce a lot of different varieties of product and hope this umbrella will encompass it. It's every single formulation you have to evaluate. And not only is that, you have to have pre-market approval before launching. And these pre-market approval can take years to do, and it's time consuming, it's costly. You could go into it, the first sort of high pressure product took 3 years to get through the regulatory process, and God knows how much money it costs them. But then you've got to start saying, well, what's the most relevant pathogen? What's the most bar tolerant pathogen? Who knows? And essentially you can get this bat and balling saying, well, have you proven it's bar tolerant? Have you proven this? And it can take years to overcome. So what we have then is the main players in high pressure. As I said, although we talk about the globe, it's really centered around US, Canada, European Union, Japan, obviously, because they were the first, and up and coming is the Australian New Zealand Food Standards Agency. And as always, they've taken a slightly different philosophy on how to approve high pressure products. As typical, US have gone alone. The US tend to go alone in sort of regulatory pathways, and in this case what they've done is saying, well, high pressures have a long history, we don't consider it novel, so you don't need to go through that process. All you have to do is show us that you can incorporate high pressure as an overall intervention strategy, which typically means 5-log reduction of the most relevant pathogen. and just illustrating that there's no post-treatment recovery, i.e. a shelf life study. No need to worry about byproduct formation, things like that. But you do evaluate on a case by case due to the knowledge gaps. But the fact is, we just did an approvals for one company. It took about 2 months to get through, and most of that time was just waiting for people to get around to look at it. If you try to do the same process in Canada, you could be spending a few years. So you just look for the pathogens of concern, obviously E. coli, salmon, Listeria most of the time. In deli meats, it's Listeria. In raw beef, it's E. coli and trim. And they've designated what log reduction, so it gives you a complete idea saying, well, this is what you have to achieve. This is a pathogen, this is the information you give us. You just give us the target pressure, the time, the come up time, decompression time, the temperature of the process, and the product formulation. Very easy, and this has really facilitated the US in expanding the high pressure. They've done it in the US. There's a lot of different products which are high pressure processed, and that list keeps growing. Very easy to introduce, and therefore the market leaders. Now in Health Canada, they've gone the opposite way. They've said every product which is put through high pressure is a novel food. So you have to go through this pre-market approval, which basically means you've got to prove there's no toxic byproducts, 5-log reduction, no change in the nutrient composition. And trying to prove a negative is very difficult. But eventually, if you climb that hill, they'll issue a letter of no objection and you can sell your wares. But as I say, it can be a very time-consuming process. So a few people have taken that hurdle of getting approvals, and the thing about high pressure processing in Canada is that you've got to really define what the process is in terms of pressure and time, and that's then set in stone. If you want to change those, you have to go all the way back to the beginning and start again in terms of validations. So what we find is that we have the sauces, etc. Applesauce was a very popular product in Canada, probably still is, which has been high pressure processed. Deli meats came because of Listeria control. Avocado, as I keep mentioning, is the sort of global runner in terms of approvals or spreading the benefits of high pressure. There's also been ground beef as a reduction step of E. coli. Certainly don't get the 5-log reduction, but it's a reduction step with shelf life. And more recently, there's been fruit, vegetable smoothies and juices. These have been shelf life extension because they haven't proven the pathogen reduction step yet. But there's a very limited list compared to the US, for example. Now in Japan, they've gone totally the opposite direction, because they said the high pressure foods are not considered novel because they were introduced in 1990. But there again, they said that, well, with so many knowledge gaps, we only can approve it for shelf life extension, and there's no approval for as a pathogen reduction step in Japan, which is again surprising given they were the ones who introduced the technology. But it's really reserved for those extension of shelf life rather than a pathogen reduction step. Now the European Union have taken a more precautionary approach, and the thing with the European Union, you have to appreciate in a lot of ways how it runs. Now it's obviously made up of member states, and those member states are governed in a way by the European Food Safety Authority. But the reality is most of these processes are SME operations, very small. It's the way Europe was historically built, and they haven't got the funds to actually bring in high pressure. But the other sort of part of it is that even though the European Food Safety Authority have this sort of big umbrella over all the member states, there's a lot of independence within those states. So, for example, if somebody doesn't like the rules of the European Food Safety Authority, then they can be challenged. And sometimes, as we'll see in pressure, you can take their advice, but you'll say, well, we're going our own way, which is exactly what happened. So it was a bit of a quandary for Europe, because they introduced a high pressure product in '95, and you can't just ban a product post-dated like that. So what they said is, we'll introduce new regulations in '97, but anything before '97, if it's been high pressure, we don't call it novel. But if anything after '97, you've got to call it novel. So you can see the dilemma they're in, saying, well, so if I bought an orange juice or another juice to the market in '98, I will go through the novel foods, but the French company producing orange juice in '95 don't have to do that. So you can see the sort of quandary. But really, one of the sort of concerns with Europe is this precautionary approach. If there's a risk involved, they always side on the side of caution. And what they said, saying, well, okay, you can apply pressure, but you need to demonstrate that there's controls in place to prevent Clostridium botulinum germinating, outgrowing. But what they did do is saying, well, yes, you can use it as an alternative thermal processing of fruit-based products only. So they were very specific in what they were going to allow and what they weren't. But as I said, the thing about member states is they can go their own way. So what the UK and Spanish did is that they went against the EU Food Safety Authority and said, okay, pressure is not novel. Obviously, the Spanish had a vested interest given that they had high pressure units who were developing them and selling them. The UK, not so much, but I guess they wanted diversity. So in the UK, they said, well, high fruit acid juices or vegetable products with a shelf life less than 21 days aren't novel, but other products are. But even then, these other member states didn't appreciate that and said, well, there's too many knowledge gaps. Like, we could even generate allergens we don't know about, and the nutrient depletion is still unknown. So, essentially what they did in the end is they said, well, we'll leave it all to the member states, as typically they would do. And they said, as long as it satisfies the microbial criteria of foods, that's similar to US and outcomes-based approach, then you can apply high pressure. But not all the member states agreed, Germany being one of them. And it's interesting, Germany have one high pressure processor and they produce hams, but not for domestic use. They have to export everything. It's actually export them to the US, oddly enough. But other sort of pressure units there is fruit juices, purees. Spain, they do ham as well, which can be sold on the domestic market, but usually it's those sort of high acid products. Guacamole is obviously the leader, and fruits extension of that. So certainly Europe have got a lot of intensive research into pressure processing. As I say, that's really the home of pressure processing, where the technology has come and have been working a lot on research intensiveness. But in terms of actual units, commercial units, it's been fairly slim pickings at the moment. Now, New Zealand and Australia, as I mentioned, they have got onto this avocado sort of processing because of its ability to preserve avocados and guacamole, extend shelf life to 4 months, and very similar to Mexico, Spain and Korea, this is what their main sort of product is, which is high pressured. But it's interesting, New Zealand Food Safety Authority have proposed some guidelines because they can see high pressure processing as a future technology. So let's get the regulations in place before we actually get the process introduced into other sectors of the food system. Now, what they've done is propose some guidelines, which is very good because, as I said, everyone's making things up as they go along these days, but at least they proposed guidelines. And they said, let's follow the US approach. Let's not worry too much about novel food products. Let's have an outcome-based approach. But where they tend to fall over then is they leave a lot of it to the processor. The processor has to justify its designation of the pathogen, but more importantly, it has to say, well, if I have this log reduction, I'm going to be safe. So it's open to question. Obviously, the processor wants to lower the log reduction due to the ability to meet that criteria, whereas the regulators want to increase it. But it's this additive approach. I think it's a case of if it's high acid, you get a certain log reduction, you've got your pressure, you've got 5 in total, you're good to go. So it's really that. But what they also get is some ideas from Europe in saying, well, regardless of what designated pathogen you use or whatever log reduction you put in, your final product has to be up to the criteria of any sort of food product. So you can't have 4 logs of E. coli, for example, and say I have a 2 log reduction, leaving 2 log E. coli in the final product. That wouldn't wash. So you have to meet that sort of criteria. And also they have to have interventions, which isn't present in the US and Canada. You don't need to have intervention to prevent germination at the moment. So, but you can see what a good thing that is to do. So in terms of the actual pressure units, they go under the Pressure Equipment Directive, which is essentially a global directive which says about what sensors, what safety measures a pressure vessel must have. And that's not just for high pressure processing, that's any pressure vessel. And also what they did to prevent people using bad foods, high pressure, and making them look good, is that any ingredients used must have the same criteria as any other product. So you can't divert, for example, a batch of trim which has had E. coli on it, and then hope to process that. For the simple reason is that you need a certificate of analysis saying it's free before you use it. And obviously it's not elastic plaster or a plaster for bad practice, so you still have to produce foods under GMP. But then what was interesting, they proposed with validation studies, which is this big knowledge gap, is that the actual process is largely down to the process to justify. So it's the responsibility of them to justify the selection of the pathogen and log reduction. So the way to do it is you'll get a product, you'll say a pathogen, you'll grow that pathogen, you'll inoculate the product, do the actual test, and then see what survives. Well, what they're suggesting is that there's so much data out there, which there is, on modelling and published reports, that you could actually use this to justify a certain process. So rather than doing all these extensive trials, etc., you can actually model it and justify through published reports. Interestingly, they say you can group products into different categories. So if you've got higher acid juice, you can say, well, it doesn't matter what high acid juice you have, you can put it under that umbrella. As we saw before, that's a dangerous thing to do due to this big variation we have in supporting the inactivation of pathogens. And you've got a no pathogen recovery over designated shelf life, which is fairly obvious. After you pressurize it, you've got to prove that what's left doesn't grow, and you've got to define obviously compression rates, packaging type, etc. So in terms of recommendations, we can see New Zealand's really at least having an attempt to get this sort of foundation to build on. And that's what you really need, because to implement novel technologies, you need to have a criteria that can be used by regulators and processors. Nobody wants to approve a process that's dangerous, which we know is not effective. But there again, we don't want to block progress. So certainly looking towards an outcomes-based approach rather than this novel food approach is a good way to go. Certainly I think we've got enough history now to say that there's not too many changes in the product in terms of allergens or making adverse effects. Well, we do get pathogen reduction. We've proven that most of the time the pathogen reduction is permanent, there's no recovery. So there's models out there, and modelling data is good because it greatly facilitates validation. Rather than doing the experiment, you can do it virtually. But there's big knowledge gaps at the moment. As I mentioned, you can produce a model that's just good for that pathogen, that strain, that product. Trying to extrapolate it to different strains even can be a problem. So it's this sort of unification of standards, because we're living in a global market, and as we mentioned, with a global market means you've got to have this level playing field. So this is what's really needed. So in terms of future, I think the food safety or novel foods designation is a barrier. It should be removed. Whether it will or not is another matter. But this outcomes-based approach definitely would facilitate it. Predictive modelling versus validation, as I said, there's too many knowledge gaps at the moment. But if we learn more about it, then predictive modelling, like we do in thermal processing, really aids things. And these additional hurdles to explore germination outgrowth are really vital, because it's those that can produce a lot of problems. So I'll talk a little bit about pressure-assisted thermal sterilisation, since it is significant. I think this technology will be surpass that of high-pressure pasteurisation. Even high-pressure pasteurisation might start creeping up with the temperature up to about 60 or 70 degrees C. Because the good thing about thermal sterilisation is that it's more predictable in some ways. It is a process that applies high temperatures, is to make a commercially sterile product. And the reason why we can use it, or want to use it, is that we can get a commercial product but have very low differences in the sensory characteristics. And this is really due to the fact we apply pressure to stabilize everything, and also we can have a quicker process. So with normal processing, thermal processing, you have this heat up time, holding time, and then obviously cooling down time. But with high pressure assisted sterilization, you have a shorter process. So a shorter process, more throughput, less changes to the sensory characteristics. So there's a lot of benefits to it, and certainly in Europe it's been researched a lot. But what we get is similar to the pasteurization, is this variation. So this is the reduction of bacillus spores, a 12 log reduction, which is equivalent to 12 commercial sterilization at 600 megapascals at different temperatures. So what we find, obviously, the lower temperature, the more time you need. But the fact is, without going to those higher temperatures, we get a product-specific inactivation. So if we're in sardine oil, the temperature required and time to get a 12 log reduction is very different for tuna, or tuna in oil, or tuna in brine. So again, it's this product-specific sort of effect that we have to overcome. And even with strain differences, so for example, with Clostridia, you'll find non-prototic strains have higher tolerance than prototic strains, and even within that you get variation with strains again. So you've got similar problems as well. And also the use of a surrogate. So sporogenes is use of a surrogate for Clostridium botulinum. Geosteriferma first use of a surrogate for canning in general. But we see they've got very different pressure tolerances when using high pressure and temperature together, which again brings up the issue of surrogates. And this is most evident with Clostridium botulinum. So Clostridium botulinum of different types, and type A is the worst one. This is the one that I've got no antidote to, and that's actually more resistant than sporogenes. So even if you inactivate sporogenes, well, you say, what happens if we get type A Clostridia involved? So as you can see, there are issues there, but thankfully they're getting ironed out, and there's going to be the first product, I think, is going to be launched, hash browns, in the very near future based on this. It's just nearly been approved by the FDA as a process for that. So certainly the first product that will produce is mashed potato. All that technology going to the humble mashed potato, but you've got to start somewhere. Certainly the focus will be on low acid foods susceptible to spore formers. The pasteurization process, as I say, is good, but if you're doing low acid foods, you're always going to get this susceptibility to pressure treatment. So there's big interest in using it for that. And as I said, Europeans are really focusing on this. They're not really that focused on high pressure pasteurization as such. It's more to do with increasing the temperature, because they know using temperature and pressure alone will give you a good product and a safer product. So I wouldn't be very surprised if we start going towards that region as well. Maybe not sterilization, but maybe using higher temperatures to do our pressure processing to try and get rid of these bar tolerances and whatnot. So in terms of gaps then, certainly what we have to think about is how does the inactivation kinetics affected by the actual unit itself? Like, is it a fact that smaller units are less efficient than higher units, or vice versa? What is the actual inactivation, mode of inactivation? If we knew that, then we could enhance the efficacy of the process. As I mentioned, a lot of people are focusing on the membranes by using lysozyme and bacteriophage to a degree. But if we knew more about it, then we could actually get more effective processes. The emergence of bar-tolerant mutants, we always seek more tolerant mutants, but there is some evidence out there that suggests that virulence and bar tolerance are inversely related. So bar-tolerant strains are less virulent, but who wants to test it out is the question. But if we knew more about what makes a mutant bar-tolerant, we could even start screening for genes, for example. Because now what we're doing is looking in the dark. We have to literally process the strain or put a strain through it to know if it's bar tolerant rather than screening for one. What does happen within high pressure is, do we get gene transfer? Do we get antibiotic resistance transfer? Do we get toxin formation by activation of genes? We do not know. And certainly that would be a good knowledge gap to know. And the big one in my mind is that we should know more about the food constituents. Like what promotes it and what goes against it, because then we can also almost engineer a food by knowing which constituents go against pressure and which ones promote it. And this standardization of protocol is vital. So we could actually engineer a bar tolerant strain for using as a surrogate, but as I say, that's way off in a way because we just don't understand which contributions contribute to bar tolerance, and certainly demonstrating equivalency to other interventions is key. So we need to show how high pressure is equivalent to a certain process to try and marry up these new novel technologies. So in conclusion, I hope I've told you that high pressure processing is a technology and processing industry that's really expanding quickly, and it's viewed to sustain its growth. There's definitely good motives to actually apply it, to be compliant with food safety regulations. There's prospects of clean labels, additive free, premium products. If you tasted, as I said, juices which have been high pressure, you can see why people will pay the extra for them. But there is big knowledge gaps exist, especially in terms of bar tolerance and interstrain variations. We're still a long way off from finding a surrogate for a lot of these processes. But as I said, I think what we will probably see in the very near future is this sort of move towards the sterilization, pressure assisted, temperature assisted pasteurization. But we'll see how the market develops.